Dynamic range. Hi, this is Gerald LeMay from Drummondville, Quebec in Canada, and this is week 4 of Introduction to Music Production at Coursera.org. In today's session, I'm talking about dynamic range. This is going to be done by way of an example. Let's say that the amplitude of the max signal level is 1,000 times the amplitude of the noise level. Then we would express dynamic range as a ratio of 1,000 to 1. For example, to be more specific, if the max signal level had an amplitude of 10,000 microvolts and if the noise level had an amplitude of 10 microvolts, then the dynamic range would be the ratio 10,000 to 10, which equals 1,000. We could also express this in decibels. 20 log base 10 of the quantity is the way we define decibels. So 20 log base 10 of the dynamic range of 1,000 would be 20 log base 10 of 10 to the third. That exponent 3 comes out in front. So we'd have 20 times 3 times log base 10 of 10. But log base 10 of 10 is 1. So we'd have 20 times 3, or 60 dB. Note that we could have also expressed this as the difference in dB. Since if you have the logarithm of a ratio of two numbers, one number divided by another number, that equals the difference between the logarithm of the numerator and the logarithm of the denominator. So 20 log base 10 of 10,000 divided by 10 is 20 log base 10 of 10,000 minus 20 log base 10 of 10. So I'm expressing 10,000 as 10 to the fourth. The 4 comes out in front, so it'll be 20 times 4 times log base 10 of 10. Log base 10 of 10 is 1. So it'll be 20 times 4 times 1, which is 80. And then minus 20 log base 10 of 10, which is 20 times 1. So it's 80 minus 20, or the 60 dB. So instead of expressing dynamic range as a ratio of two numbers, one number divided by another number, if these quantities are expressed in dB, then we can express this as the difference of two quantities. There's a rule that's very useful in dealing with digital quantization of numbers, and that's the 6n dB per bit rule, and it relates directly to dynamic range. First of all, to figure this out, to understand it, the max signal level of an n-bit word is 2 to the n minus 1. So this simply means that if we had, for example, a 3-bit word, then the available numbers would be 0, 1, 2, 3, all the way up to 7. So thus, in our context of max signal level, 7 would be the max signal level. And you'll note that 2 to the n minus 1, where n is equal to 3, is 2 to the 3 minus 1. 2 to the 3 is 8, so 8 minus 1 is 7. If there's an error in the first bit, then the noise level is in the first bit. And that simply means that either a 0 should have been a 1 or a 1 should have been a 0 in that first bit. So the difference in the noise, so to speak, in either case is 1. Thus the dynamic range, which is the ratio of max signal level to noise level, expressed in dB, is 20 log base 10 of that ratio. So it would be 20 log base 10 of max signal level, which is 2 to the n minus 1, over the noise level, which is 1. But 2 to the n minus 1 is approximately 2 to the n for large n. So 20 log base 10 of 2 to the n minus 1 over 1 is approximately 20 log base 10 of 2 to the n. That n in the exponent comes out in front, so we have 20 times n times log base 10 of 2. Log base 10 of 2 is approximately 0.3, and 20 times 0.3 is 6. So we end up with 6n. Thus the dynamic range is 6n dB, which means that we have 6 dB per bit. So if we had a 16-bit A to D, then the dynamic range would be 6 times 16, or 96 dB. While if we had a 12-bit A to D, the dynamic range would be 6 times 12, or 72 dB. If our signal has a dynamic range that exceeds the dynamic range of our A to D, then we can compress the dynamic range of the signal. And that's what was discussed in this portion of the course. This usually means that the amplitude above a certain threshold is attenuated linearly, so that the resulting dynamic range of their signal will fit the dynamic range of the A to D. I really like expressing mathematical background of concepts such as dynamic range, and in this short presentation, some of this background has been presented. Thanks for taking the time to check this out.